Welcome to lesson 5-3 on conditional probability. Free tacos. In 2012, fans at the Arizona Diamondbacks home games would win 3 free tacos from Taco Bell if the Diamondbacks scored 6 or more runs. In the 2012 season, the Diamondbacks won 41 of their 81 home games and gave away free tacos in 30 of their 81 home games. In 26 of the games, the Diamondbacks won and gave away free tacos. So I fill in all these squares. 26 of the games, Diamondbacks won and gave away free tacos. In 30 of the games, they gave away free tacos. In 81 home games total, and they won 41 of their 81 home games. So after I have a bunch of those boxes all filled in, I can subtract to fill in the rest. All right. Find the probability that the Diamondbacks win or there are free tacos. So they win 41 games. They get free tacos at 30 games. We have to subtract the intersection of 26 games. So we get 45 out of 81 or 0.56. Find the probability that the Diamondbacks win given that there are free tacos. So I want to find this notation here, that they win given there's free tacos. In this case, I'm going to cover up some of the table. I want to know only that they win given there's free tacos. So I'm only considering these 30 games where there were free tacos. What's the probability they won given there's free tacos? What's the probability they win out of these 30 games? That's 26 out of 30. 0.87. So I'm finding a new total, and that comes from given tacos. Okay? So I'm only interested in all the times that there was free tacos. Okay. Find the probability that there are free tacos given the Diamondbacks win. So now this is a different given. Given they win means I'm covering up this part of the table, and I'm going in this direction, and I'm only considering of these 41 games. So given they win, there's free tacos at 26 of the 41 games, which gives us 0.63. Okay, what is the conditional probability? Is there a formula, and is it on the formula sheet? Okay, so the conditional probability means that the probability of A given B. So that's the probability of A and B happening out of all the times that B happens. So we really see that given B, we're only looking at the table total for the events that B happened. So given is this bar, so the probability of A given B. We're really just finding the probability of A in the circumstance that B happened. Okay, break down a table. Okay. Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there is a 9.90 probability that she makes it to class on time. However, if she hits the snooze bar, there is only a 0.70 probability that she makes it to class on time. Okay, so use a tree diagram. So first we have Shannon's alarm goes off. Then 60% of the time she snoozes and 40% of the time she does not snooze. When she snoozes, she has a 0.7 probability of being on time and a 0.3 probability of being late. But when she doesn't snooze, she has a 0.9 probability of being on time and a 0.10 probability of being late. Realize that these out here are already conditional probabilities. What's the probability that she snoozes? What's the probability that she's on time given she snoozes is already out this way, okay? So 70% of the time she's on time given she snoozed, okay? All right, on a randomly chosen day, what is the probability that Shannon is late for class? She's late for class 2 ways, when she snoozes or when she doesn't snooze. So what we'll do is if we want to go out the branch and out that branch, we're going to take 0.60 times 0.30 because 0.6% or 0.6 of the time she is snoozing, and then 0.3 of that time she is late. Okay, she also does not snooze and is late, 0.4 and 0.1. So I'm going to take 0.6 times 0.3 and add it to the other scenario, 0.4 times 0.1, and I get 0.22. Suppose that Shannon is late for school. What is the probability she hits the snooze bar that morning? Probability she hits a snooze given she's late is probability of snooze and late over late. So we will just consider 0.6 times 0.3 over 0.22 because snooze and late. Given she's late is right here. Okay, so out of all the ways that she's late, what's the probability that she snoozed? So we go out this 0.6 way, and then we remember that she could have been late 2 different ways. Okay, so 0.82, and it's really common for the questions to be progressive like this. What is a general multiplication rule? Is it on the formula sheet? The probability of A and B is the probability of A times B. Okay, and that's the probability of A times the probability of B given A happened. When is it better to use a tree diagram than a two-way table? Tree is when the chance process involves a sequence of outcomes, like first she's going to snooze, then she'll be late. But a two-way table is all situations otherwise, like we just have 2 variables, period. Below is a two-way table created in an earlier example that displays the results from a random sample of 500 people's high school graduation and home ownership status. So let G be high school graduate and let H be homeowner. Find the following probabilities. The probability of being a grad is 310 out of 500. The probability of being a homeowner is over here, 340 out of 500. The probability of not being a graduate means that you are 190 out of 500, and the probability of not being a homeowner is 160 out of 500. The probability of being a grad and a homeowner is a grad and a homeowner, that's 221 out of 500. The probability that you didn't graduate but you're a homeowner is 119 out of 500. And the probability that you graduated given you're a homeowner means I'm going this way, and given I'm a homeowner, I'm only looking at homeowners then, and the probability that I graduated is 221 out of 340. And the probability that you are a homeowner given you did not graduate. So we're going to go to not graduate, which is 190 people, and the probability that you are a homeowner that you did not graduate is 0.63. Okay, independence. Many employers require prospective employees to take a drug test. A positive result in this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs, then false positive rate is 5% and the false negative rate is 10%. Make a tree diagram of this chance process. So employees are drug tested. We know that 0.4 of prospective employees use drugs, and then therefore 0.96 don't use drugs. And if the false positive rate is 5% and the false negative rate is 10%, then we know that we're going to get a true positive of 90% of the time and a false negative 10% of the time. Okay? And then if the false positive is 5%, then the non-drug users are going to get a false positive 5% of the time and a true negative 95% of the time. What percent of prospective employees will test positive? Okay, so the probability of a positive test happens 2 ways. You use drugs and you test positive, or you accidentally get a false positive when you're not a drug user. So 0.04 times 0.9 and 0.96 times 0.05 is 0.084. What percent of prospective employees who test positive actually use illegal drugs? The probability they use drugs given a test positive is the probability the user is a user and positive over all the people that are positive. So we have all the probability that they're positive, and we now want to know what's the probability they actually use drugs given they have a positive result. So we get 0.43. So given a positive result, there's really only less than half of those that actually use drugs. So this is a pretty bad test. Okay, tattoos revisited. Let's revisit the male versus female with or without tattoos, shown as a two-way table. Okay, part A. What is the probability that a randomly selected person has a tattoo given they are male? And how would you denote the symbols? I would denote it like this. Probability of tattoo given male is a probability of tattoo and male over male. So tattoo and male over male is 19 out of 90, which is 0.21. Okay, create a conditional distribution of the tattoo for each gender and graph with a segmented bar graph. Okay, so then male and female and yes and no, we think that first somebody has a certain gender, then they have a tattoo. So to make a conditional distribution, I'm going to say that first they're a certain gender, then they have tattoos. So if this variable comes first, I'm going to divide in its direction, which is to divide down. So I take 19 out of 90 and 71 out of 90 and 84 out of 88 and 4 out of 88. And I get these here. Okay. And so then these are my, this is my segmented bar graph. For segmented bar graph, they always go up to 100, which represents 100% of the people in the study. And so 100% of males, we only had about 21% of them have tattoos. And for females, we had 95% of them have tattoos. The media survey that went out in 2017 to all RB students included 33% freshmen, 32% sophomores, 21% juniors, and 14% seniors. For the freshmen, 88% of these students used haiku 3 days per week in decreasing fashion, and 68% of sophomores used haiku 5 days per week, and only 31% of juniors and 9% of seniors used haiku 5 days per week. Suppose that we selected one student at random. So first we can select a freshman, sophomore, junior, senior, then we can see if they check haiku 5 days a week. Find the probability that this person used haiku 5 or more days per week. The probability they check haiku 5 or more days per week for freshmen, sophomores, juniors, and seniors turns out to be 0.59 probability that happens. Given that this person used haiku 5 days per week, what is the probability that he or she is an upperclassman? So the probability of upperclassmen, given they check haiku, is going to use this probability rule. Probability of A given B equals the probability of A and B happening over the probability of B. That's the probability of upperclassmen and check haiku over the probability of check haiku. So if that's all the people that check haiku, then that goes down there. And the probability of upperclassmen in check haiku is the juniors that check haiku and the seniors that check haiku. So 0.21 times 0.31 and 0.14 times 0.09. Okay, so that's 0.13. All right, so how can you tell if two events are independent? If knowing the outcome of the first event doesn't provide information about the second event, think about coin flips and die rolls and card draws with replacement. They're similar to a scatter plot with no association. So two events are independent if knowing the first one tells you nothing about the second one. Knowing the x variable still doesn't give you any clue about the y variable, because for low values of x, there are low and high values of y, and for high values of x, there are low and high values of y. Okay, so that would make those two events independent. The probability of A given B is equal to the probability of A, and same thing for the reversal. If you knew B happened, it still won't change the probability of A happening. Okay, so it's kind of like having a boy first and curious what the next gender is going to be. It really doesn't make a difference what the first gender was. The second gender still has the same probability of being either gender. Okay. In the Diamondbacks example, there are events T, which is free tacos, and W, which is win. Are they independent? Okay, so the probability of win given tacos, is it equal to the probability of win? Is the probability of A given B equal to the probability of A? So let's check out win given tacos, and then let's check out win. Win given tacos was 26 out of 30, which is 0.87, but the probability of win is 0.51. So you know now that if tacos were given away, that it's more likely that the team won. The events T, free tacos, and W for wins are not independent. The probability that the Diamondbacks win a game, given they gave out free tacos, is 0.87, which is 0.36 greater than the probability of Diamondbacks simply winning a game, which is 0.51. Ashford did a study, she really didn't, with all 315 students that she had in her class over 2 years. She took note of each student's gender and which hand they used to write during their first quiz of the year. She found the following data. So 315 students total. I have males and females, left-handed and right-handed people. Okay? So are gender and handedness independent? The probability of male given left-handed is equal to the probability of male. I'm going to test that. So male given left-handed is 14 out of 30. And the probability of male is 147 out of 315. And that's 0.46 repeating. Okay, so they're both actually 0.46 repeating. 14 out of 30 gives me 0.46 repeating, and 147 out of 315 gives me 0.46 repeating. So that means that these are actually independent. Knowing one does not tell me anything more about the other. So left-handed and gender is independent. Yes, gender and handedness are independent. Knowing the person's gender tells us nothing more about the person's handedness. Okay, I did it the other way just to show you that it really doesn't matter which variable you choose at all. Okay, in this two-way kind of table, 2 by 2. So the probability of left given male is equal to the probability of left, just like the probability of male given left is equal to the probability of male. So left given male is 14 out of 147, and the probability of left is 30 out of 315, and so those two decimals are exactly the same. The following is a table about the region of the country someone is from, limited to West and South only, and their preference of music given the two choices, country and rock. Are these events independent? Okay, so is region and music preference independent? So I'm just going to grab two variables, country and Western, and see if it's the same as country. So if you are from the West, is the probability that you like country the same as if you're just anywhere from the table liking country? So country, given you're from the West, is here 26 out of 44. And the probability that you like country is 57 out of 107. So those two are not equal. So no, the events country and lives in the West are not independent. Knowing that the person lives in the West increases the probability that the person likes country music. Okay, so because one tells us a little bit about the other, then they are not independent events. What is the multiplication rule for independent events, and is it on the formula sheet, and how is it related to the general multiplication rule? The multiplication rule for independent events is just a little bit shorter. It's a probability of A times B, and that's it. And remember from page 12 that the general multiplication rule is the probability of A and B happening. That's the probability of A times the probability of B given A. So we want to make sure that when we use the probability of B, that it's the conditional probability that B happened given A happened. But when they are independent events, the probability of B given A is the same as just the probability of B, so we don't need to consider that whole like given A part. So the probability is just probability of A times the probability of B, where the general multiplication rule is the probability of A times the probability of B given A. So we're just going to fill in a table so that A and B are independent. So that means that we want 18 out of 30 and 60 out of 100, that those two fractions are equal. So 60 out of 100 is equal to 18 out of 30, or 18 out of 60 is equal to 30 out of 100. Okay, the first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a false positive result. Among 100 women with normal pregnancies, what is the probability that there will be at least one false positive? So 1 minus the probability of no false positives, okay, is the probability, and also the probability of a false positive is 0.05, and the probability of no false positives is a 0.95. Then we want 1 minus the probability of no false positives to the 100th power, because we want 100 no false positives. and then we're going to do 1 minus that. And so 1 minus this is 0.994, and that represents getting at least one false positive. So that means 1 false positive, or 2, or 3, or 4, or 5, all the way up to 100 false positives. Okay. Weather conditions. On a recent day, the Northwest Herald forecast a 50% chance of rain in Crystal Lake and a 50% chance of rain in Richmond. What is the probability that it will rain in both locations? The probability it rains in Crystal Lake and Richmond, we actually are not given the intersection. The conditional probability. So the probability of A and B equals the probability it rains in Crystal Lake times the probability it rains in Richmond given it rained in Crystal Lake. But we aren't given that probability. That's probably pretty close to like 80-90% chance or something like that. But the chance here will increase because we know that it rained in Crystal Lake. And so if the storm hit Crystal Lake, it might be a little more likely that it also hits Richmond. So we weren't given this conditional probability. These are not included independent events. So if it rains in Crystal Lake, the probability it rains in Richmond is probably greater than 0.50. Okay, so for independent events, you can just take the probability of one times the probability of the other. But the nature of this is that if there's a storm cloud over Crystal Lake, it might now be more likely that there's also going to be that same storm, or that the storms have come this far south, or that the storms have come this far north, or whatever, and it might increase the chance that there's also a storm cloud or the same storm cloud over Richmond. Okay. For each chance process, determine whether the events are independent and justify your answer. Shuffle a standard deck of cards, then turn over the top card. Put it back in the deck and shuffle again, and turn over the top card again. Define events A, the top card's a heart, and B, the second card is a heart. These are independent events because replacing the card. Knowing the first card will not help you predict the second. Both have a probability of 1/4, probability of heart, and a probability of heart given a heart is still 1/4. Now shuffle a standard deck of cards and turn over the top 2 cards one at a time. Boom, boom. Okay, they're both laying there. Define events A, the first card's a heart, and B, the second card's a heart. These are not independent events. The probability of the second card being a heart will change depending on the first card. The 28 students in Mrs. Pitchford's AP Statistics class completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. Choose a student from the class at random. So male, female, right-handed, left-handed. The events of interest are female and right-handed. Are they independent? I will keep that one. Probability of right-handed given female equals the probability of right-handed. Remember, it doesn't matter which one you go first or second. So just go ahead and choose a conditional format. Probability of right-handed given female equals the probability of right-handed, or the probability of female given right-handed equals the probability of female. Okay, so 18 out of 21 are right-handed given female, and 24 out of 28 are just right-handed. And are those truly equal? Yes. Knowing someone is female doesn't change the probability that the person is right-handed. What is the difference between mutually exclusive and independent? Okay, so let's go back to the definition. Mutually exclusive means 2 events cannot occur together. So probability of A and B both occurring is 0. But independent means knowing the result of one event tells us nothing more about the other, so therefore they can occur together. So mutually exclusive would be like a red card and a club, because clubs are black cards. These are mutually exclusive because they cannot occur together. They are not independent, however, because if event A occurs, the probability of B changes to 0. So if you draw a card and it's a red card, the probability that it's also a club is 0. Okay, so the probability of B is 0.25, but the probability of B given A is 0. They are not equal, so they are not independent events. Okay, but they are mutually exclusive events. So we have yes, mutually exclusive, no to independent. Okay, let's talk about two independent events though. A red card and a 7. Well, now these are not mutually exclusive because there's an intersection. They can occur together. There are 2 red 7s in the deck. And these are yes to independent. So now we have no to mutually exclusive and yes to independent. Knowing you have a red card doesn't change the probability that it's a 7. The probability of B given A equals B. The probability of it's a 7 given it's a red card is 2 out of 26, and the probability it's just a 7 is 4 out of 52, and those are equal. Okay, so then another scenario is that it's neither mutually exclusive or independent. So the probability of a red card or the probability of a heart, these are not mutually exclusive. All hearts are red, so they both happen together. And it's not independent because these are different fraction values. The probability of a heart is 1/4, and the probability of a heart given it's a red card is 1/2. Okay, so those are your 3 situations. You have either mutually exclusive events that are not independent, or you have independent events that are not mutually exclusive, or you have not independent and not mutually exclusive. But they can never happen together where you have independent and mutually exclusive. Okay. Choose a U.S. adult at random. Define event A, the person is a male, and B, the person is pregnant. Are these events mutually exclusive, and are they independent? Mutually exclusive, yes. The events are mutually exclusive because you cannot be both male and pregnant. Independent, no. These events are not independent. Knowing the person is pregnant changes the probability that they are male. Mutually exclusive events can never be independent. Handedness again. All right, so here we have another handedness of 100 people, and let's try it again. Is gender and handedness independent? So the probability of left-handed given male equals the probability of left-handed. Left-handed given male is 0.15 because out of all the males, the left-handed males is 7 out of 46. But the probability of left-handed is 10 out of 100. Ooh. So there's a 0.15 probability that you're lefty given you're a male, but there's only 0.1 of the probability of being left-handed altogether. So if you're a male, you're more likely to be left-handed. No, these 2 events are not mutually exclusive. Knowing the gender is male increases the probability the person is left-handed. Okay, 2 events A and B are blank if the occurrence of one event does not change the probability that the other event will happen. 2 events are independent if the occurrence of one event does not change the probability of the other event happening. Longest finger, ring or index? For me, my ring finger or index. My ring finger is just a tad bit longer than my index finger. Okay. So to find out, we use the random sampler at the United States Census at School website to select 452 U.S. high school students who completed the survey. The 2-way table shows the gender of each student and which finger was longer. They're on their left hand, index finger or ring finger. So that hand. Ring finger longer than index finger. Okay. Are the events female and has a longer ring finger independent, and justify your answer? So we're going to go ring finger given female versus the probability that ring finger is longer. And I defined both my variables, which is very important to get your full points. Then you can go ahead and use notation with just letters. Ring finger given female is 82 out of 212. And is it truly equal to the probability of, in general, the ring finger being longer, 234 out of 452? So we get 0.38 and 0.51, quite different numbers. No, the 2 events are not independent. Knowing that the gender is female decreases the probability of a longer relative ring finger. According to Forrest Gump, life's like a box of chocolates. You never know what you're going to get. Suppose a candy maker offers a special Gump box with 20 chocolates that look the same. In fact, 14 of the candies have soft centers and 6 have hard centers. Choose 2 candies from the Gump box at random. Draw a tree diagram and that shows the sample space across the chance process. The implication here, even though it doesn't say with or without replacement, the implication is that you're eating the first candy, then you're taking the next candy out of the box, and then you're eating the next candy. So we think we're drawing without replacement when we're taking candies from a box of candy. Choose the first chocolate. Here's the different types of centers. Then choose the second candy, and if a soft center is taken, then there's one fewer candy, and especially one fewer soft center, but still just as many hard center candies. And if a hard center candy is taken, then there's one fewer candy in the box, so we're now at 19 candies, and especially one of the 6 hard candies is gone, but we still have all 14 soft center candies. Okay, so find the probability of drawing 2 chocolates such that one of the chocolates has a soft center and the other one doesn't. So that can happen in 2 ways. First a soft, then a hard, or first a hard, then a soft. Okay, so when I say or, I mean plus sign, and when I say and, I mean multiplication, and there we go, 0.442 for find the probability. Suppose you take 2 gum boxes and choose 2 random chocolates from each. What is the probability that you get 1 soft and 1 hard center from each? Assume the boxes are independent. The probability of 1 box is 0.442. The probability of 2 boxes is the probability of box 1 and box 2 doing the thing. That means box 1 getting a hard and a soft and box 2 getting a hard and a soft. So it's 0.442 times 0.442, which is 0.195. Suppose you take a sample of 100 gum boxes of chocolate and repeat this process again. What is the probability that you get 1 soft and 1 hard center for all 100 boxes? Approximately 0. The first trimester screen is a non-invasive test. Okay, so let's get down to the nitty-gritties here. Now let's change the numbers around a little bit. The false positive rate is about 0.007. This is the latest first trimester screen now, the most current one. The false positive is 0.007. Among 100 women with normal pregnancies, what is the chance that there will be at least 1 false positive? So we're going to do the same steps. The probability of no false positive is 0.993 then, and the probability of at least 1 false positive is 1 minus the probability of no false positive. So after we have these kind of rudimentary steps kind of worked out and have our brains around it, no false positive, at least 1 false positive is 1 minus the probability of no false positive, and we want 100 of no false positives. And if you have 100 straight tests that read correctly, then that would be ideal. But in this case, we're thinking that we had any scenario but that. So we're taking 1 minus the perfect scenario of 100 tests reading out correctly for 100 healthy babies. So that's 0.505 still, that at least 1 test is going to have a false positive. There's a 0.505 probability of at least 1 false positive in 100 normal pregnancies. Okay, that is it for us. Thank you for watching.